Hello and welcome to this video. This one will probably be a little bit longer because it's a spring mass example, and those tend to be kind of complicated. So for this one, we want to find the simple harmonic motion equation of a spring mass system and the damping classification, given that m equals 1/4, c equals 3/4, k equals 1/2, x of 0 is 2, and the v of 0 is 0. This will be our change in distance. This is our velocity, our initial conditions for those. So the idea is, we want to find some spring mass equation x of t, and that's a simple harmonic motion, and then we want to do our damping classification. There's three kinds of damping. We'll have critical, and then overdamped, or we'll have underdamped. And how you know you have each of these cases: for critically damped case, we have repeated roots. And then for overdamped case, we have our distinct roots. And then for underdamped, we have complex roots. Okay, also butting in here real quick, I wanted to make sure we have this covered. For each of these three cases, there are different general solutions, so this is very important to know. So for our critical point, or our critical damping, we have our repeated roots. That's when we have critical damping. The general solution using these roots, so we'll have e to the negative at, and then unknown constant 1 plus unknown constant 2 and t, where a will be our repeated root. And then for overdamping, we'll have distinct roots. So our x of t, like we'll go through in this example, has c1 e to the r1t plus c2 e to the r2t, where r1 and r2 are our two different roots, and c1 and c2 are some unknown constants that we'll have to find. And then for underdamping, we have complex roots, and for this we'll go through in our second example here, but we have an x of t equals to c e to the negative at cosine of omega 1 t minus alpha, where a is our root, or at least the real part of our roots, and then we'll go through it here in just a minute. So the first step is we need to find an equation to work with, and to do that we will always have this basic equation where we have mx double prime plus cx prime plus kx is equal to 0. This will be our generic spring equation every time. And the next step, what we want to do is we'll plug in all our values. So we find that we have 1/4 x double prime plus 3/4 x prime plus 1/2 x is equal to 0. And then now this is basically just another simple equation where we want to do a substitution. So we're going to let x equal to e to the rt. So x prime, taking all of our derivatives, we find is r e to the rt. X double prime is equal to r squared e to the rt. We want to substitute these in to our equation. So we'll find we have 1/4 r squared. I'm going to factor out an e to the rt because each of these have an e to the rt in them. So I'm going to factor that out. And then we have a 3/4 r, and the r of t is factored out, plus a 1/2 e, and then again it's factored out. And we don't need to worry about this because we're looking for non-trivial answers. So basically you can ignore that, it's gone. And now we want to set this equal to 0 and factor it. So we're going to have 1/4 r squared plus 3/4 r plus 1/2 is equal to 0. I'm going to multiply everything by 4 to get rid of that fraction. So we have r squared plus 3r, and then plus 2 is equal to 0. If I go to factor this, I get 2, and then so 2 and 1 adds back to 3. So therefore I have r plus 1. I'll have r plus 2, where r is either -1 or -2. And so we have two distinct roots, which therefore means we have an overdamped case. So therefore, a general solution for an overdamped case will be x of t is equal to some unknown constant. I'll say it's c1 e to the r1t, which is this our first root, plus some unknown constant, another one, a different one, so c2, then e to the r2, which is our other root, t. So our next step is we want to find these unknown constants. We have our roots, so I'm going to do x of t is equal to c1. I'm going to plug in my first root, which is -1, so I can just write minus t, because 1 times t is t. And then I'll have plus c2 e to the root 2, so I'll have a -2t for my other root. And then remember from the beginning that we have x of 0 is equal to 2. So what I want to do next is I want to plug that in using that initial condition to find an equation for our constants. So x of 0 is equal to 2, so I'll have 2 is equal to c1. So the 0 goes in for t, and e to the 0 is just 1, so they basically drop out. So we are left with c1 plus c2 equals 2 for one equation. And we need to find another equation, but thankfully we were given another initial condition. But to use it, we need to take the derivative of this equation to find our v of t, because this is basically like our position function. Take the derivative, you get your velocity function. Take the derivative of that, you get your acceleration function. We just need velocity, so we're going to take one derivative. So we'll have v of t is basically equal to x prime of t, however you want to denote it. And then we find that we get negative c1 e to the negative t, and then minus 2 c2 e to the negative 2t. And remember v0 is equal to 0 from our initial condition. So we're going to plug that in. So I have 0 is equal to, again, e to the t. E to this, it becomes e to the 0, so it's gone. So we just have a negative c1 minus a 2c2, because this one goes away as well. So therefore we have c1 is equal to a negative 2c2. And if we plug that into this equation over here, we'll have 2 is equal to negative 2c2 plus c2. So 2 is equal to a negative c2. And then once we have that, we find that c2 is equal to a negative 2 for one of our constants. And then we want to take that, plug it back in here to find our c1. If we do c1 is equal to negative 2 times negative 2, we find that c1 is equal to 4. And therefore our spring mass equation will be x of t is equal to 4 for our c1, e to the negative t, because remember that was our first root. And then we want to do minus 2, because that's our c2. And then we'll have e to the negative 2t, because that was our second root. And that is the general solution to this equation. Okay, so for our second example, basically all we're going to change is we need to find x of t when c is 0 now instead of 3/4. We're going to switch it to 0. The rest will stay the same. So the first step, again, is we want to go through our general spring mass equation setup. So we have mx double prime plus a cx prime plus a kx is equal to 0. In this case, this will be 0 because we have c equals equal to 0. Then we'll plug in 1/4 for our m, so an x double prime plus a kx, so we'll have 1/2 x equal to 0. We're going to let x equal to e to the rt again, so x prime equals to r e to the rt, and then x double prime is equal to r squared e to the rt. So I'm going to plug those in now. So I have 1/4, and I'm going to factor out the e to the rt because both x and x double prime have it. So e to the rt, and then we'll have an r squared plus 1/2 equals 0. And again, this can go away because we're looking for non-trivial answers, so this doesn't matter. So now we have just this, so 1/4 r squared plus 1/2 equals to 0. Multiply everything by 4 to get rid of that initial value. So we'll have an r squared plus 2 equals 0. So now we find that we have r squared equals to negative 2. If we take the square root, can't do the square root of a negative number, so we have r is equal to plus or minus square root of 2i. And with that, we now have a complex root. So if we remember, we would be underdamped because we have complex roots. So this will be our general solution here. But I'm going to have to write it in a different format to get started, and then we'll eventually convert it into this format. So I'm going to run through how to do that right now. So for our general solution, we're going to have x of t is equal to a cosine of square root 2t plus b sine of square root 2t, where a and b are some unknown constants. So for this, we remember that we had the same initial condition that x0 is equal to 2, because all we've changed is that c is equal to 0, so I can keep this. So if I plug that into this equation, I find that 2 is equal to a times 1 plus b times 0. So if we plug in 0 for t, cosine of 0 is 1, sine of 0 is 0, so that goes away. And then we're just left with a is equal to 2. And then what we need to do is we were given our other initial condition, v of 0 equals 0. And remember that we have this position function. Take the derivative, we get our velocity function. That's great because that's what we have an initial condition for. So v of t equal to x prime of t is going to be equal to square root 2 times a, and then we'll have sine of square root 2t. Don't forget your negative because cosine, derivative of cosine is a negative sign. And then we'll have plus square root 2b cosine of square root 2t. And so v0 is equal to 0 from our previous example. And plugging this in, we find that 0 equals negative square root of 2a times 0, because sine of 0 is just 0. So that'll end up going away. And then we have square root of 2b times the cosine of 1. Or excuse me, not cosine of 1, cosine of 0, which is 1. So if we simplify this, this goes away because it becomes 0. And then if we just divide everything by square root of 2, we find that b is equal to 0. So knowing that, we can plug this into this equation now. And I am going to plug in the 0 just because it'll make it easier. And I'll show you why here in a minute. So we have 2 is equal to a, so I'll plug that in. Cosine of square root 2t plus 0 sine square root 2t. There we go. Okay, so the next step is we need to find something that we can factor out. And this is often denoted as c is equal to a squared plus b squared, all in square root. We need to use this format to find whatever value c is to pull out of the equation. So if I plug in 2 for a, because that's what a is, and I plug in 0 for b, square them both and square root them both, I find that I get 4, because this will just be 0, this will be 4, so I just end up with the square root of 4 equals c. So c is equal to 2. So if I factor out a 2 from this equation, I'll have x of t is equal to 2 multiplied. So if I factored it out, 2 times something gives me 2 cosine of that. So I will end up with a cosine of square root of 2t. And then I have 2 times something gives me 0, which is 0. So I will have plus 0 over 2. We'll just write it like that. Sine of square root 2t. So this will just be simplified to 0. And then there will be just a 1 here in front. And then the next thing I need to do is a trig identity. So this is where it gets a little tricky. So for our first one, that's cosine alpha. The second cosine here is cosine beta. This 0 will be sine alpha. And then our sine term will be sine beta. And so the trig identity we're going to use is cosine of alpha minus beta is equal to cosine alpha cosine beta multiplied by cosine beta, and then plus sine of alpha, sine of beta. Okay, so since x of t is equal to 2 times cosine alpha cosine beta plus sine alpha sine beta, I'm going to plug all that in here, and then I'll rewrite it so that x of t is equal to this format instead. So by doing that, we get x of t is equal to a 2, which remember was our c value. C was 2, so we're going to put the 2 there. Then cosine of alpha minus beta. And for beta, we already know this one because we have cosine of beta and sine of beta. So beta is the square root of 2t. So I'm going to plug that in for beta. So x of t is equal to 2 cosine of alpha minus square root of 2t. And this is an even function, so because cosine is the even function, you can rearrange these and just flip them. So I will change it to x of t equals to 2 cosine of square root of 2t minus alpha. And that's our general solution format that we wanted from before, but we need to find our alpha term. So to do that, we do have cosine alpha equals 1 and sine alpha equals 0. So I will write cosine alpha equals 1, and then I'll have sine alpha equals 0. We take alpha equals cosine, the inverse cosine of that, and then alpha is also equal to sine inverse of 0. Find that alpha is equal to 0 in both cases, which is great. These should match, so you know that you have the right alpha. And another term is alpha is in radians, just so you know. Gotta remember that as well. So alpha is in radians, and these should match. You can use them from this format. And since our alpha is 0, we'll have x of t is equal to 2 cosine of square root 2t. That's our final answer for this problem.